Hey guys. So now we're going to kind of move on and start taking a look at uniform circular motion. When I first started teaching physics, I actually had this as a whole separate unit, and we talked a little bit more about gravitation here, which we'll go ahead and definitely cover next week. We'll go ahead and take a look at Newtonian gravity and gravitational interactions. But I want to go ahead and start that section of mechanics 2 today. And so we're going to take a look at uniform circular motion. Remember, this is periodic, so that means it's going to be something that repeats. It's going to happen again and again and again and again. And that we're going to have to separate out circular motion from linear motion, which is what we've been covering up to this point. So if you think about our, velocities, accelerations, things like that that we've been calculating so far, we've been looking at them in terms of linear velocities, so in a straight line. So in circular, that's a little different, and we have to think about angles, arcs, these types of things. So let's go ahead and jump in and take a look at our essential questions. So our first essential question is, what is periodic motion? Now, I answered a little bit of that already, but I want to make sure that you understand what a periodic motion is. Number two, in which direction does a centripetal force or centripetal acceleration point to? If you break down that word centripetal, I think you can already answer some of that question as well. Number three, what is the difference between rotating and revolving? Now, I first got introduced to this when we were going ahead and taking a look at the demotion of Pluto. And so I'll probably bring that up later when we get to that so you can understand the difference and why it matters quite a bit. Number four, what two factors does an object's centripetal force depend on? And number five, what is centrifugal force? All right. Before we go ahead and start getting into the actual periodic motion and looking at calculating universal circular motion, I want to do a really quick review of Newtonian forces. So remember that when there is no external force, an object will travel in a straight line, right? This is according to Newton's first law of motion. In order for an object to travel in a circle, though, there has to be a force on it that makes it travel in that circle. And because it's changing direction in terms of its straight line trajectory, that means that there has to be a force acting upon it. And if you take a look at the cars here on the right, you've got your one on the left, which is going straight, linear motion, and your one on the right, which has an arc shape to it, which has circular motion. And that also has that inward pointing vector representing that centripetal force. Now, if you were driving in the car, we can kind of think about this test that you can go ahead and do. If you're going to go ahead and turn and you think about the ball, the bowling ball, let's say, that's in the middle of the bed of your truck, that ball is going to go ahead and roll as you go ahead and stop the car. But if you think about your car as being in a different frame of reference than the ball and you follow the ball is going to appear to go in a straight line and the car is going to change directions. This should make sense because this is inertia. The object in motion is going to want to stay in motion in the same direction with the same velocity unless a force acts upon it. Now, this is going to change direction if you turn your car and it hits the side wall of the truck and starts bouncing in another direction. But if we deal with something that's repeating itself, okay, this is what is called a periodic motion. So remember back to when we talked about projectile motion. Projectile motion does not repeat and therefore is not periodic. It goes up, reaches a peak, comes back down, and stops. But we said that we can also relate projectile motion into orbits. And if an object is fired up with enough velocity, it escapes the strongest gravitational pull of the planet and gets to a point where gravity matches. So the amount of falling that the object does matches the curvature of the path of its trajectory, and then it orbits. Okay. An orbit like this would be considered a periodic motion, something that repeats. So think about like our planet going around the sun, the moon going around our planet, okay? Or even our solar system going around the galactic bulge. Now, this is possible because of what we call centripetal force. An object in circular motion always tries to move in a straight line, according to Newton's first law, the law of inertia. However, there is a force that acts towards the center of motion. Now, when we deal with planets or when we deal with stars, this force is gravity. That creates this centripetal or center pointing force that makes the object travel in that circular path. It could just as easily be friction, however, that causes this when we start thinking about running around a banked track, for example. The banking, the friction of the banking, and this is important when we start designing things like roads. So if you're thinking about a career in, like city design, that type of engineering, civil engineering, you need that force to help maintain safety, to go ahead and keep the arc continuing in terms of the movement. Well, we can go ahead and calculate using this. When the centripetal force is too strong, the ball will accelerate towards the center of the circle. When the centripetal force is too weak, the ball will get out of orbit and it will continue on a straight path. This is true for any object that's experiencing a centripetal force. Okay? It will only continue on that circular pathway. It will only continue on that circular pathway when the centripetal force is well balanced. And so we can use this formula below to calculate the centripetal force. F equals mv squared over r. Now, we will take a closer look at this equation, F equals mv squared over r, but this is essentially derived from Newton's second law. And so if we were to go ahead and break this down, you can probably understand part of this already. Okay, so we have F, which represents our force, equals m, there's mass. And so in this case, if we're relating this to F equals ma, a, or centripetal acceleration, which we'll run into a little bit here, is equal to v squared over r. Okay, so r representing the radius and v the velocity, and we'll talk a little bit more about that here in a minute. Okay. Now, this is where these terms come in, and this is important if you're interested in astronomy and trying to understand the difference between a dwarf planet versus a traditional planet. The point or line that is the center of the circle is the axis of rotation. If the axis of rotation is inside the object is said to be rotating or spinning on its axis. If the axis of rotation is outside of the object is then revolving. So let's go ahead and take a look at this and talk a little bit about Pluto and Charon and why we end up demoting Pluto to a dwarf planet. Okay, so if I go ahead and talk about the Sun Earth system, we can go ahead and draw a little circle here. We'll call this the Sun, and we have another little circle here that's the Earth. With respect to the size of the Sun is massive compared to the Earth. And so the orbit that the Earth is going to go ahead and take, and it's actually elliptical, not really circular, is such that the axis of rotation is inside the Sun. So because of that, we say that the Earth revolves around the Sun. Now, the Sun is a star, which is huge, it's massive, even though it's a main sequence yellow star, so it's actually pretty small as far as stars go. But when we go ahead and take a look at this pathway that we have Earth traveling is a revolution because the axis of rotation is inside the Sun. Now, we see the same thing if we go ahead and take a look at the Earth with respect to the Moon. The Moon is so much smaller than the Earth is, so the axis of rotation is internal. Now, this is going to be different when we go ahead and start taking a look. So if we take a look at the relationship of Pluto and Charon, for example, okay, It turns out that the sizes are not large enough. So if we make that Pluto and that Charon, that the axis of rotation is no longer inside Pluto. Okay, so Pluto would be a planet if it dominated its own orbit and the axis of rotation were internal. But between Pluto and Charon, even though it favors Pluto, the axis of rotation is external to the planet, which means that they both orbit a point in space, not the moon orbiting the planet. And because of this, this is one of the key reasons that Pluto was demoted to a dwarf planet, is that it does not dominate its own orbit. Okay, so revolution occurs when something orbits around another object with an axis of rotation inside the other object, versus revolution. When we start looking at this type of revolution, they're revolving around something external in space, but since it's not internal, this is not a traditional planet, but a dwarf planet instead. Okay, so we can think about spinning. If there's my axis, it spins on its axis, internal axis of rotation. Revolution around an external point, whether that external point is inside another object or whether that external point is between objects. Okay, so this is another place where the center of mass ends up being important, because this plays a role in terms of where that point of rotation is going to occur. And there are a lot of these circular motions throughout the universe. Okay. All right. So let's go ahead and talk a little bit more about centripetal acceleration and centripetal force. The acceleration of an object moving in a circle is always going to be pointed towards the center. So a centripetal force or a centripetal acceleration means center pointing. So if we go ahead and take a look at that equation that we had from before, right? We had F equals mv squared over r. This is for force centripetal. And we said that if we use Newton's second law, F equals m, then the part that's missing here is a, which is represented here. So a centripetal is equal to v squared over r. When we start looking at that, this is how we're going to go ahead and calculate or come up with this particular equation. Okay. So the centripetal acceleration depends largely on two pieces. One, the speed of the object, represented here by v squared, and the radius of the circle. So the farther out you are, right, what that's going to do is that's going to go ahead and change the centripetal acceleration. And so we can use this to better understand how satellites move around our planet and other things along these lines. Now, if we bring in Newton's second law, it says that if an object is accelerating, there must be a net force. For an object moving in a circle, this is called the centripetal force and calculated as we showed you before. The centripetal force also always points towards the center of the circle. Okay, centripetal force, centripetal acceleration always point towards the center of the circle. Now, in order to make an object revolve around an axis, the net force on the object must pull towards the center. And this is the centripetal force, or center seeking, okay? Center pointing. Now, when we look at the force, which is slightly different from the acceleration, remember acceleration depends on speed and radius. The centripetal force depends on the object's mass, because it's mass times acceleration, and the object's speed. Okay, so the faster it's traveling, the more force it has. But the centripetal force also depends on the object's distance from the axis. So this is that radius. If the linear velocity is held constant, more distance requires less force. If rotational velocity is held constant, more distance requires more force. So this is a point where we're going to go ahead and look at a difference between linear velocity and rotational velocity. And this is a point where your degrees or your radians comes into play. Okay? When we start taking a look at this, we have to visualize in terms of a circle. If this is my circle, linear velocity is just traditional distance. If I cover more distance, okay, if we have the same this, we're going to go ahead and require less force if we're covering the more distance. But if we're dealing with rotational, we need to think about this in terms of the angle. This angle is the same whether you're internal or external. But because we're dealing with the same angle covered, the greater distance requires more force. All right. So when we go ahead and take a look at this, F centripetal, as we said before, equals mass velocity squared over r. So v squared is going to represent a linear velocity. We can also use m equals r omega squared, where omega is going to represent an angular velocity. They're still going to be based on the distance, but the relationship is different if we use angular velocity as opposed to linear velocity. Now, as we get to the end of the term, we're going to be looking at force and its relationship with things like work. Work is a relationship to energy because you need energy to do work. And so when we start looking at work done by centripetal force, since the force on an object is always perpendicular to the object's velocity, the centripetal force never does any work on the object. No energy is transformed doing this. So if you ever try and do this, you can go ahead and put an object. What we do in class typically is we'll go ahead and put a rubber stopper and we'll put it on a string and start spinning it in circles. Okay. Once you get it going, it requires almost no work for you to keep it there. Okay. We may have to go ahead and move our wrist a little bit to keep the same angular velocity, but the idea is different because the motion that you're doing is not necessarily in line with the actual thing done. And we'll talk more about this when we get to work later on. Another thing I hear a lot, and so that's why I've started including it in my notes, is well, you get thrown off of a merry-go-round because of centrifugal force. Well, centrifugal force is not real. It's a fictitious force. It is not an interaction between any two options and therefore not a real force. Nothing pulls you away from the center of the circle. So a lot of people say, I was thrown off the merry-go-round because of centrifugal force. No, what happened is your inertia wanted you to keep going forward. And if you let go, your forward path took over rather than the force of the centripetal force keeping you in the circle, and you just kept going. So what is misattributed to the centrifugal force is actually the action of inertia. Okay? And that's because your linear velocity wants to continue in a straight line. If we go back to our example from before where you're spinning over your head a rubber stopper or something on the end of a string, and I just keep going in circles and circles and circles, it'll keep going in a circle. But if I were to go ahead and have a sharp blade up there and then the rope hits that short blade that's holding the stopper is going to take off in a straight line, not a curved arc, but a straight line from the point where the rope broke. Okay. This is kind of the idea of how a sling works. You think about the old stories of David and Goliath. The sling goes ahead and goes in a circular motion to pick up speed. And then when you release one side of the sling, it causes the rock to travel in a straight trajectory so that you can try and attack your enemy. All right. This is inertia, not centrifugal force. So let's really quickly talk about how this applies to a car so you can kind of see how this works in your day-to-day life. Remember, we said that when you turn a car, you're changing direction and therefore you're accelerating. Well, now we know why. Because in order to turn that, you need a force, and in this case, it's going to be a centripetal force. All right. So, what is the physics behind this event? The diagram below shows a car, the blue rectangle, going around a turn. This is a top view, but there must be a centripetal or center pointing force on the car in order for it to maintain the curve. This centripetal force can be created in a number of ways. But you have to remember that acceleration is a vector quantity, meaning it has magnitude and direction. So we know that no matter what else is going on, a turning car is accelerating even if its speed is constant. And this is because of the changing of the direction. So Newton's second law says that accelerations are caused by forces, and if that acceleration is caused by causing the change by pulling it towards the center, then the force has to be pointing also towards the center. We also know that forces are interactions between objects, so there must be something else that's exerting the centripetal force. It doesn't just magically happen. And what is exerting the centripetal force on the car? Well, that depends on the situation. So let's start with a situation where you don't have any banking. Okay. You're going down the road and you need to make a right turn. Okay. If the ground is level, the downward force on the car is caused by its weight. The upward force is the normal force of the road, and those two are going to be perpendicular. Well, the normal force is perpendicular to the surface it's on. We know that the car is not accelerating up and down because the vertical and the two vertical components of the force are canceling each other out. So Newton's first law tells us that these two forces must cancel so that the vertical net force on the car is zero. We also know, however, that there must be a horizontal net force on the car in order to get it to turn. A force is needed to make the acceleration happen, Newton's second law. This force is the centripetal force, and the friction force points down towards the center of the turn and is responsible for turning the car. So you turn the wheels of the car, and the rubber on the tires, the point where that meets the road, is creating friction, and that friction is creating that center pointing force, which is what is accelerating the car. So in an unbanked turn, the force responsible for turning the car is friction. Okay. To see how this works, think of what would happen if there were no friction. Would you be able to turn your car if, let's say, the roads were super smooth and icy? Now, some of you may have driven in the winter and you've had this sort of experience, and you try and turn the wheel and the car just keeps going forward. It doesn't turn to the right because there's not enough friction between the tires and the road to actually create the centripetal force which turns the car. Okay. This is why if you try and panic when you're in an icy situation, there is not enough friction, so you have to slowly ease into things. Any quick movements are not going to be recognized and you head into the ditch. Another very important feature of this diagram is that there is no outward pointing force. So there is no centrifugal force. It is simply the inertia of the car, right, wanting to continue in a straight line. So what have we figured out here? The normal force, which is perpendicular to the ground, and the weight, which is your mass times gravity, cancel each other out. So again, there is no vertical component. Okay. If there is no friction, there is no force to supply the centripetal force, and the car can't turn unless we have a banked turn. Now, why is banking good? If the car is on a banked turn, the normal force, remember, is still in a perpendicular direction from the surface. All right. Because it is no longer perfectly straight up and down, it does not cancel out the weight of the object. Because of this, if we break our weight down into component vectors, x and y, and use the surface as our frame of reference for our coordinate system, you end up with a component that does cancel out the normal force and another component that's pointing inward. Let's go ahead and take a look at this. So if we take a look at this particular example, I'll try a different color this time. If we take a look at this example, we can break this up, okay, into two component vectors. One that's going to go this way, which will cancel out the normal force, and one that's going to go this direction, and that's pointing down the slope. Well, look at that. We have just created, using gravity, an F centripetal. This is the portion of the gravity that creates the centripetal force that's going to keep the car turning. So this is a very important thing to do when we go ahead and take a look at designing major curves, especially in the mountains or something like that. Now, there are instances in our country, we actually have an example here in Eugene, where we did not build the roads to have this type of bank to it. And so there isn't an assist to the turn because of the bank creating a centripetal force due to gravity. So if you've ever taken, um, there's Old Dillard Road, which kind of runs a back cut from, say, um, Amazon Parkway. If you head south and start going to like Cresswell or Goshen, okay, there's a little back road that's called Old Dillard, and it kind of winds and snakes. And there are a couple of sections on it where if we use the same car, for example, okay, excuse my drawing, but if this is our car and it wants to go ahead and turn, say we're going this way, well, instead of the bank being like this, like it should be, the bank to the road is like this, which is actually trying to force a centripetal force this way, even though the road is turning to the right. This is a horrible design from an engineering perspective because you're actually encouraging people to go off the road because of the design of the road. Okay. So keep that in mind. This is why you have curves. Now, I used to run track all the time. And one of the things that's very different about indoor track versus outdoor track is because it's such a short track, they get a lot of speed to them and they tend to bank the curves so that people stay on the track. They don't do this with outdoor track, which has a big circumference. But it takes several laps around an indoor track to match up to a single outdoor circumference. All right. So a car on level surface, all forces are vertical, so no horizontal can be generated unless we go ahead and add friction because of the tires. A car on a bank turn, however, the normal force will not match the weight. It'll only match a component of the weight, which creates a centripetal force. And that horizontal component of the normal force is what's going to go ahead and create the centripetal force. Okay. Now, suppose we consider a particular car going around a particular bank turn, and the centripetal force is needed to turn the car. Mv squared r depends on the speed of the car. So there is an optimal speed for driving a corner, right? And you can kind of feel this if you get a really good bank on a curve. If you hit the gas, it causes you to kind of slide up the curve because you're going faster. If you ease off the gas, it causes you to kind of slide downhill towards the center. And I don't know if you guys have ever played any one of those video games like Gran Turismo or something like this. It's a racing game. You can definitely experience this. The higher your speeds are when you go ahead and hit those terms, you can feel the car sliding up the embankment or down the embankment depending on its velocity. So every curve is designed with an ideal speed at which it keeps them perfectly in the center and they continue on at the same velocity, same speed, but changing their direction. Okay. So when we start thinking about this in the right diagram, okay, the velocity is greater than the ideal speed. And what you end up seeing with is that the car is going to want to slide uphill, up the incline. But if your velocity is less than the ideal speed, the left diagram, then you end up with a car that's going to want to slide down the incline because the friction on the tires is going to be greater than the velocity going forward, and it's going to start to pull towards the center because of the center pointing force. Okay, there's the force of friction. So here are our key concepts. This is probably the most important slide from this presentation. So let's remind ourselves of some of our geometry, and then we can think about some of these with respect to the physics you've learned today. First of all, circumference. If we're thinking about distance, if you want the circumference of a circle, it's 2 pi r. Acceleration is changing even if speed is not, because direction is. Remember, it's a vector quantity. To calculate a change in velocity, we have to use vector addition. Acceleration, centripetal acceleration, is going to be v squared over r, which is 4 pi squared r over t squared. Okay. And if you have questions about how that works out, you can come into office hours and we can go over it. And then F centripetal or centripetal force still is Newton's second law, F equals ma. But in this case, A is v squared over r, which we just showed above. So F centripetal equals m v squared over r, or equals m times 4 pi squared r over t. All right, so let's finish up with giving you guys a practice problem. So go ahead and take a minute, pause the video, and try this. A 900 kilogram car moving at 10 meters per second takes a turn around a circle with a radius of 25 meters. Determine the acceleration and the net force acting upon the car. So in this case, we're looking at a circle. So we have a radius, and we're going to be looking at circular motion. So first of all, we're trying to find the acceleration. This is centripetal acceleration. And we end up getting 4 meters per second squared. Okay. So when we do the force centripetal, we end up getting 3,600 newtons. So how did we get that? So when we go ahead and do this, we need to go ahead and follow the steps that we just talked about before. So F equals ma. Okay, we're trying to find the centripetal force. So the first thing we should always do is find the mass and the acceleration. Well, we have the mass right here. So we need to find the acceleration, but we just said that for a centripetal, it's going to be equal to v squared over r. Now, we're not talking to you about what angle is covered in what amount of time. So this is going to be a linear velocity. So this is 10 meters per second squared over the radius, which is 25 meters. Okay, 10 times 10 is 100. So a centripetal is equal to 100 meters squared per second squared, because we did our squaring, over 25.0 meters. One of the meters cancels, one of the meters cancels. 100 divided by 25, a centripetal is equal to 4 meters per second squared. Our units are correct, matches our answer from over here. Excellent. Well, now we can simply use this number and substitute that in with our mass to find our force centripetal. So F centripetal is equal to the mass, which we said here is 900 kilograms, times the acceleration, 4 meters per second squared. And if you go ahead and do the math, nine times 4 is 36. So 3,600 newtons. Okay, guys. Good luck with the worksheet. If you have any questions, please don't hesitate to come see me. Stay healthy, stay safe, and we'll talk to you soon. Take care, guys. So long.